Today we want to calculate some more line integrals. We have a new vector field, we'll call it G, and it's going to be 2xy I hat plus x squared plus 2y times j hat. I think this is going to do what I want it to do. X squared y. That should work. So we have multiple paths. We've got this parabola, we've got the line, and we've got the circle that we parameterized yesterday. We're going to calculate the line integral of this vector field over these three different paths. So let's just get to calculating. So we're going to do the integral over C2 of G dot dr. And I guess it'll be dr2. So C2 is parameterized by the path t squared and t. So C2 is, we'll call it R2 of t, is t squared in the xi plus t for the yj, and this is for the values of t between 0 and 1. So what we have is our x is the t squared and y is t. So x of t is t squared and y of t is t. That's the path, the first path we're doing. C2 is the parabola t squared comma t. So t squared I plus t times j. That's our parameterization of the path C2. So we need to evaluate the vector field G at these at this x and y. So the vector field G is 2 times x times y. So I'll have the I component is 2 times x, which is t squared, times y, which is t. That's the I component, and the j component is x squared times y plus 2 times y j. All that is just the vector field G evaluated at the parameterization of our curve. Now I need the dot product of this with r prime of t. So if r2 of t is t squared I plus t times j, our dr will be just the derivative. So 2t times I plus 1 times j, and all this multiplied by dt. The question is, it's a dot product, so how much of one vector is going in the direction of the other vector? How do these two vectors combine for this direction that the path is taking? So we have the dot product of the function evaluated at all the points on the path and the 2ti plus 1j. And we do this for all the values of t that tell us where the path is. And those values of t are from 0 to 1. at every point on the curve, we're looking at the vector from the vector field. Here's the vector from the vector field at all the points on the curve. And here is the direction of the curve. And I want to know how much is going in the direction of how much of one is going in the direction of the other. Now we need to calculate the dot product. So I multiply the I components and multiply the J components. I'm going to clean this up a little bit because it is rather messy, but I've got 2t cubed in the I direction. And I've got t to the 5th plus 2t in the J direction. That's just a simplified vector field at all the points on the path. We still haven't integrated with respect to t yet. We are calculating the dot product. So the next stage is to calculate the dot product. So I get this 2t to the 3rd times the 2t. So that gives me a 4t to the 4th plus t to the 5th plus 2t plus 1. Oh, times 1. This is all dt on the outside, and we integrate from 0 to 1. So now we can integrate with respect to t. We've done the dot product. So now we can do our integration with respect to t. I've got 4/5 t to the 5th plus 1/6 t to the 6th plus t squared evaluated from 0 to 1. Now you might be thinking, man, Leach, you really took it easy on yourself by integrating from 0 to 1. We always had that power. T going from 0 to 1, that was part of our choice in parameterizing the curve. So the way I took it easy on myself was making the starting point at 0, 0 and the ending point at 1. So I can easily plug into 1. I still got to add fractions, which is unpleasant, but I just got to do 4/5 plus a 6th plus 1. So 4/5 plus 1/6 plus 1. So what is this? 24 30s, 5 30s, and 30 30s. So 30, 54, 59, 59 30s. Minus 0 30s. Thank you for checking. I'll trust myself. Any questions? Same thing that we've been doing this week. We've been evaluating line integral. We want to remember what the parts of doing this are, evaluating the vector field at every point along the path. The path, t squared I plus tj, that describes the path. Those are the points that we're plugging into the vector field. The vector field is telling us about vectors all over the plane. I want these that are along this path. And I also want to know what direction that path is headed. That is going to be the derivative of that path. And so I want the dot product between the vector field, what the vector field is doing at all those points, and what the path is doing at all those points. I want to find that dot product for whatever reason our dot product is represented. So mechanically, we're doing the same stuff that we were always doing with integration. Even way back to how do we measure speed in chapter 5 of this variable. We just do distance is equal to rate times time at all the different times that we're concerned with. But we have more ways, more than one way to get from the point 0, 0 to the point 1, 1. We got 59 over 30 for this path from 0, 0 to 1, 1. Let's integrate over the line C3 of G dot dr3. So now our path looks different. So R3 of t is just the line ti plus t times j. Our interval is still the same. T goes from 0 to 1. Our dr will look different. Spelled equals wrong. Equals is the side note. Now I need to evaluate the vector field G at each of the points. So in this case, X and Y are both T. So X is equal to T and Y is equal to T. So we're going to have the integral of 2 times T times T I plus T squared times T plus 2 T J. This is my vector field evaluated at all those points. X is equal to T. And Y is also equal to T. For some reason, I felt the need to color code the different T's. Here's our vector field evaluated at all the points along this path. And we find the dot product with the direction of the path, which is going to be 1i plus 1j dt. I'm going to do the same thing I did last time. I'm going to clean this up a little bit. So this is going to be a 2t squared I t cubed plus 2t times j. We still haven't integrated anything, so I still need that. Oh, I forgot to put my endpoints. We're still integrating from 0 to 1. So now I need to calculate the dot product, which is just going to be the product of the I components, 2t squared times 1, so 2t squared. And the t cubed plus 2t times 1. And so this is the function that we're going to be integrating. Pause for copying. I don't read that part of the telecom. Question. Yep, so we're gonna have what, 12s we'll use, 8 12s, 3 12s, and 12 12s. Yeah. Yeah, 2 and negative 112. Oh, I did this wrong. I did it wrong in the exact same way. Anyone see what I did wrong? Man, I'm gonna have to edit this out. So notice here, I've got x squared and I've got this y. I wrote x squared y plus 2y, and that is not what we wanted. It's supposed to be x squared plus 2y. And I did it again down here. So this is good. Plus I hat. Plus, this is where the mistake shows up. I have to have a t squared squared, but not this t here, plus 2t. Yep. Well, nothing to do but go back and fix it. So let's fix it. So we've got a 2t to the third I hat, and then here we have just a t to the fourth plus 2t j hat. All right. I think I got it fixed now. I'll edit that out later. Actually, no, I won't. That would be way too much effort. We can't be afraid to make mistakes. All right, so now let's calculate the dot product. So I got 2t cubed times 2t. That's going to be 4t to the fourth. That makes sense because that's not where I messed up. And then t to the fourth plus 2t instead of the t to the fifth. So I've got 5t to the fourth now. Integrating 5t to the fourth is going to be a t to the fifth. And integrating 2t is going to give us a t squared. There's that extra 1/30th. Yeah, it's recording.
Oh, I didn't see the screen.
Yeah, the screen lower has slipped a little bit. No, we have 5t to the fourth. We add one of the exponents. We have 5t to the fourth because I got 4t to the fourth plus t to the fourth. That's going to give me 5t to the fourth. So I integrate that to t to the fifth. And then the integral of 2t is the t squared. We got to fix the other one because I did the same thing in the second one on the second path. Because, I mean, I looked at the 59/30. I'm like, oh, wait a second. Maybe I made a mistake earlier. Then I just. That's this term, but there's also this 4/5 t to the fifth. So there's one of them. I combine these two, it's 5t to the fourth, and then it gives me a t to the fifth. All right, we got to fix the other one too. Yeah. So g is 2xy plus x squared plus 2y. And then my other dot product here with the dr, which is 1i and 1j. Let's pick this second one. So we'll integrate from 0 to 1. Let's see. Let's clean this up. We've got 2t squared I and t squared plus 2t times j. Now we find the dot product and it's multiplying both by 1. So we just get 2t squared plus a t squared plus a 2t dt. This 2t squared and this t squared make a 3t squared plus the 2t. So I'm integrating a t to the third plus a t squared from 0 to 1, and we get 2. 2 again. Because now I started using the vector field that I had intended to use, not the one that I had messed up. The lesson here is when you're reviewing the problems that you want to do, finish the problem. Don't just say, oh yeah, this is working out, and then move on. Or at least check what you're doing when the number comes out a little bit spicier than you thought it was going to be. So what we want to notice here, before we move on to C4, is that we got the same value. Now that we're using the correct vector field, we got the same value from along our two different paths. Along the parabola path, we got a total value of 2, and along the linear path, we got a total value of 2. Anyone want to guess what will happen if we go along the circular path? Probably going to be the same. At least it was intended to be the same. So if we look at our vector field, so this is super suspicious that they came out the same. It's also super suspicious that I went back to fix them. I knew there was something wrong when it said 59/30. That's what I knew, but I'm like, oh, I'll just go on anyway. And then the back of my mind was like, well, where are you going to get the 5 for the denominator? It'll be fine. And then it wasn't fine. So the reason that this worked out the same is that the vector field that I chose which is 2xyi plus x squared, just x squared, plus 2yj, is a gradient field. So I built this vector field. Well, actually, I designed the vector field to be the gradient of one function. So this vector field has a potential function. And that's why we got the same amount. Potential functions, or sorry, vector gradient fields are path independent. Gradient fields are path independent. Another word for path independent is conservative. So gradient fields are conservative fields, path independent. All that matters is the endpoint. The function g of xy is known as the potential function. That's the potential function for the gradient field g. So if we look at the two components of the vector field G, if G is going to be the gradient of some scalar function G, some potential function, that means that the 2xy is the derivative of the potential function with respect to x, and the x squared plus 2y is the derivative of the potential function with respect to y. So let's integrate with respect to x. So this tells us that the function g of xy, I'm going to integrate with respect to x, and I'll get an x squared times y. We're treating the y as a constant factor. When we integrate, we end up with some constant. But we're doing a partial derivative. So this constant could just be a regular old constant, but it could also be a function of y. Because the derivative with respect to x will treat a constant or a function of y as constant. So this plus c could represent a function of y. Because the derivative with respect to x will treat a function of y as a constant term. If the derivative with respect to y is x squared plus 2y, then g of xy will have to have the form x squared y. That matches up. And the integral of 2y is y squared. Plus some constant, which could be a function of x. So putting these two pieces of evidence together, we can see that the x squared y matches up. The y squared that we got from the gy of xy must be the constant term that shows up in the gx. So it looks like our g of xy, our potential function, should have the form x squared y plus y squared plus some constant. So for C4, we have a much more complicated path that we were not going to want to plug in and then integrate. But we now see we don't have to. There'll be like cosine squares and stuff like that. But now we see we don't have to because we have a gradient function. Any path from 0, 0 to 1, 1 through this vector field will give us a line integral of 2. Any questions? All right. Unfortunately, I had to take some time to fix my mistakes because I wasn't being careful enough, I guess. But we do want to combine this with our fundamental theorem of calculus for line integrals. The integral over some path C of a gradient function dot dr will just be the potential function evaluated at Q minus the potential function evaluated at P. So if I evaluate this function at the point 1, 1, I get 2. If I evaluate the function at the point 0, 0, I get 0. The difference is 2. All right, that's going to do it for today. That's going to do it for this week. I'll post some new homework. Everybody have a good weekend. See you Monday, and thanks for playing. See you on Monday.